Hello! We've been working on quantizing angular momentum. We show that the total angular momentum operator and its z component commute with one another. We computed the eigenstates for angular momentum, first abstractly and then in space in terms of spherical harmonics. Later, we computed the kinetic term in a Hamiltonian and showed that it contains the total angular momentum operator. Today, we want to leverage both of those things in order to study hydrogen. We started this course with a problem of the classical hydrogen atom and showed that it was unstable. Then, we spent weeks developing quantum mechanics. We're finally in the position to resolve the hydrogen problem, but to do so, we need to solve for the states. And in order to solve for those states, we want to leverage what we already know. Our strategy for attacking the problems that we've been studying in quantum mechanics is to first think about commutation relations. We had before that if we use a coordinate basis in spherical polar coordinates, the total angular momentum operator takes this form. If you look at this form, you can see that it involves only derivatives with respect to theta and phi. When we had trouble before, it was when we did things like examine commutators involving x and its derivatives, for example, x with its own momentum. Those gave commutators that were non-zero. Here, the coordinates that we're using are r, theta, and phi. The total angular momentum operator that we've written down here commutes with anything that involves only r and r derivatives because the total angular momentum operator involves only derivatives with respect to theta and phi. What that means is if we had a potential energy u, which was a function only of the radial coordinate, people sometimes refer to this as an isotropic or centrally symmetric potential, we could write the form of the Hamiltonian for a problem that looks like that. In this form here, where we have some terms that I've highlighted in red that involve only radial parts, and then the blue part here involves the total angular momentum operator. What's the point of this? Well, if we stare at this expression for a moment, we can notice that because the rest of the terms in the Hamiltonian that don't involve the total angular momentum operator are a function only of r, they must commute with that total angular momentum operator. That suggests that states can have fixed angular momentum and energy at the same time. We also studied before the z component of the angular momentum and found that its position space representation in spherical polar coordinates was given by this form here. That means that in addition, the z component of the angular momentum also commutes with all these radial parts of the Hamiltonian. That means that states not only can have fixed total angular momentum, they can also have a fixed z component of the angular momentum. States can be eigenstates of the radial part of the Hamiltonian and the total angular momentum and its z component. This allows us to narrow down the form of the states. We're going to make a guess for the form of these states where n, l, and m index the eigenvalues for the Hamiltonian, the total angular momentum, and the z component of the angular momentum. This gives us three criteria for our states. One is that the total Hamiltonian acting on the state gives the energy of that state indexed by n. The next is that the total angular momentum operator acting on the state gives the form that we had before, h bar squared l times l plus 1 acting on the state. And the z component of the angular momentum gives h bar times m. Our goal is to find the form of the states that allow us to make this true. We're going to work in the position basis, so we're going to represent our states by a sum over our wave function coefficients expressed in terms of r, theta, and phi, times a ket vector that represents a particle sitting at position r, theta, and phi. Now we need to find the form of our wave function psi sub nlm as a function of r, theta, and phi. These three criteria on the energy, the total angular momentum, and the z component of the angular momentum suggest that we guess a form for our states where we have a function capital R that is a function only of the radial coordinate, and the angular coordinates, theta and phi, are captured by our spherical harmonics that we computed previously. So why would we take this form? This satisfies our properties for the total angular momentum and the z component of the angular momentum because we constructed the spherical harmonics specifically to satisfy those properties. If this form of the solution works for the total Hamiltonian, that is, it solves the Schrödinger equation, then we're all set. In order to verify this, then we have to work out the Schrödinger equation. We had before that the total Hamiltonian for the system takes this form here. Next, we need to substitute the wave function into the Schrödinger equation. The expression is long, but it looks like this. The first thing that we can notice is that it involves the total angular momentum operator acting on the spherical harmonics. We can apply the total angular momentum to the spherical harmonics and use the fact that we know that it's an eigenvector and simplify our Schrödinger equation by inserting the eigenvalue. The next thing we can notice here is that the spherical harmonics are a common factor in all of the terms of our Schrödinger equation, allowing us to cancel them out. When we cancel them out, we get a simplified Schrödinger equation that involves only the radial function capital R and radial derivatives that looks like this. By making the substitution for the form of the spherical harmonics that we found, we got an ordinary differential equation for this function capital R. Now we need to solve that ordinary differential equation. If this ordinary differential equation has a solution, then the form that we proposed for psi was a good ansatz. If it doesn't, if it leads to a contradiction, then we made a bad ansatz. Fortunately, this is going to work out for us, although it's going to take some work to figure that out. The first thing that we should notice here is that the equation for capital R does not have any m dependence anywhere. Mathematically, that means that we can just drop the m index on our function capital R because it's irrelevant. Physically, that means that the energy of all the Lz eigenstates are going to be the same. In order to solve the hydrogen atom, we're going to have to insert the Coulomb potential into our Hamiltonian. The Coulomb potential has this form here where little e is the electric charge and 4 pi epsilon naught is the electric permittivity. If we substitute this Coulomb potential into the Schrödinger equation, then we get an ordinary differential equation for R that looks like this. In order to solve this, what I'm going to do is I'm going to bring everything that doesn't have a derivative to the right-hand side and rearrange a little bit to get this equation here. Now, before we go further, I want to pause and use dimensional analysis to try to investigate the form of this equation. The Schrödinger equation that I just wrote down had this form here. And the first thing that we can notice is that all of these terms on the right-hand side have dimensionless coefficients. The first thing that we're going to do is we're going to introduce a characteristic length called the Bohr radius. We're going to get that Bohr radius by examining the R term in the differential equation. By making the identification that mu, the mass, times epsilon squared r over 2 pi epsilon naught h bar squared is 2r over this quantity a naught, which is the Bohr radius, that allows us to describe the characteristic length scale in the system. It turns out that if you substitute in all these physical quantities, you find that the Bohr radius is on the order of 10 to the negative 11 meters. The next thing that we want to do is determine the characteristic energy. Epsilon, we're going to define the characteristic energy implicitly through this expression down here on the bottom left. We can do some rearranging of that expression to find that the characteristic energy scale epsilon can be written as the mass times the fourth power of the electric charge over some constants that involve h bar squared, and if you put in real units for this, you get it's minus 13.6 electron volts. Now let's think a little bit about the energy for a moment before we go on. The Coulomb potential has the property that it goes to zero for very large r. We want to study bound states of the electron, meaning they can't escape to infinity. That means that the energy of our state has to be less than the potential energy as r goes to infinity. That means that for all the states that we're interested in, the energy has to be less than zero. That makes sense then that our epsilon that we defined on the previous slide is negative. Now what we'd like to do is substitute our characteristic length and energy into the Schrödinger equation. To do that, we're going to define a dimensionless radius, rho, that's the ratio of r over a naught, and a dimensionless energy that I'm going to call u sub n squared, that is the negative of the energy over epsilon. When we substitute these things into the Schrödinger equation, we get this. This is the thing that we need to solve. It's not an ordinary differential equation that we probably know the solution of off the top of our heads. What we're going to do is to try to find limits where we can solve that. Then we're going to piece the information together to get a full solution. The first thing we're going to do is we're going to study the problem near the origin, rho equals 0. The ordinary differential equation we had looks like this. If we examine the terms, we can notice that this first term is constant in rho, the second term is linear in rho, and the third term is quadratic in rho. What this means is if rho goes to 0, or equivalently r goes to 0, the leading term in the differential equation is just given by the constant term. This gives us what mathematicians sometimes refer to as an additional equation. We're going to propose that capital R goes like rho to the alpha. Then we can differentiate the left-hand side using that guess, and find that the left-hand side has to be equal to alpha times alpha plus 1 times rho of alpha. Now if we look at the right-hand side, we realize that that's just L times L plus 1 times rho of alpha. In order for those two things to be the same, we have to have that alpha equals L. Physically, what that means is that the small r behavior, or the behavior near the origin, is determined by the angular momentum. We had an ordinary differential equation that looks like this. If we think about the rho dependence of the terms, again we have a constant, a linear, and a quadratic term, and if now we're thinking about the limit of large rho, what that means is that the only term that matters here is the rho squared one. Now capital R has to go to 0 as rho goes to infinity because we can't have the particle escaping. So we might ask ourselves, well, what is the form of capital R? It could go to 0 like a power law, it could go to 0 exponentially, it could go to 0 in some other way. What we will try is taking capital R proportional to e to the minus beta rho. If we substitute this in and look at the leading order contribution for large rho, what we find is that beta squared rho squared e to the minus beta rho from the left-hand side has to equal u sub n squared rho squared times e to the minus beta rho from the right-hand side. And what that tells us is that beta squared has to be u sub n squared, or beta has to be u sub n. What should we do now? Well, we found the solution for small rho is capital R goes like rho to the L. We found the solution for large rho that capital R has to fall off exponentially. We need the solution for moderate rho, or rho's in between. We're going to guess the form of the solution that looks like this. This form takes capital R is the product of the form for small rho, the form for large rho, with some function f of rho in between that's going to allow us to interpolate between these two extremes. This interpolating function f of rho has to satisfy some specific criteria though. It can't mess things up as rho goes to 0 or rho goes to infinity. What this means is that f of rho has to be a constant as rho goes to 0, so it doesn't disturb the rho to the L behavior we found before. It also means that f of rho has to be a polynomial for large rho so that it doesn't disturb the exponential fall-off we found before. Before we continue, I want to note that we don't know what u sub n is yet. This is like what we had before in other problems where we found that matching conditions determine the energy. Here we're going to need to solve the matching conditions between small rho and large rho in order to determine the energies. Now, we're going to continue, but what we need to know is what is the ordinary differential equation that f of rho satisfies. To find the ordinary differential equation for f that allows us to solve it, the first thing that we're going to do is we're going to substitute f into the left-hand side of the Schrödinger equation. The first thing that we're going to do is we're going to differentiate with respect to rho. That gives us a whole bunch of terms. Then we need to differentiate with respect to rho again, and that gives us even more terms. Then we need to compare with the right-hand side. Substituting the form of our solution into the right-hand side, we get something that looks like this. If we make a comparison of the left-hand and the right-hand side, we see a whole bunch of terms that I've highlighted here in red that are common between the two, and we can cancel those out. Comparing the left-hand and right-hand side then gives us this ordinary differential equation for f. The ordinary differential equation we have for f has this form here. It's not very nice, so the first thing I'm going to do is simplify and rearrange it. In order to solve this, I'm going to look for a power series solution of this form here. If I substitute that into the ordinary differential equation and start differentiating, I get something that looks like this. You might remember from your study of ordinary differential equations that in order to solve ordinary differential equations using these power series expansions, we need to solve a recursion relation for the coefficients. In order to do that, I'm going to re-index the summations here. You can notice that all the powers of rho here are not the same between the various terms, and so I want to make them the same by re-indexing the summation. A valid solution for this ordinary differential equation satisfies the recursion relation between the coefficient c sub j plus 1 and c sub j that involves all of these constants. The recursion relation we just wrote down on the previous slide looked like this. We had the requirement that f of rho had to be a polynomial as rho went to infinity in order to not disturb our exponential fall off. That can only be true if the series terminates. That means that we have to have some coefficients in this series equal to 0 for some large j's. In particular, we must have c sub j plus 1 equal to 0 for some j. For that to happen in turn, that requires that our recursion relation has to have a 0 in it for some particular j. The way that we can do that is by making the numerator of this recursion relationship 0. The way that we can do that is by making the numerator of the recursion relationship 0. And that can happen if u sub n is 1 over 1 plus L plus j. That fixes the energy. Now that we've fixed the energies, we want to determine what they are. We found that u sub n was 1 over 1 plus L plus j. We can write that as 1 over n if we refer to n as 1 plus L plus j. Substituting in the fact that we know the scale of the energy as epsilon, we can write the energy in the form of epsilon times u sub n squared. And inserting the constants for epsilon, we find that this is minus 13.6 electron volts over n squared approximately. Next, we can work out the possible values for the energy. The smallest energy corresponding to the ground state occurs when L equals 0 and we terminate the series for F after one term. That corresponds to n equals 1, and the n equals 1 state energy is just epsilon, which is minus 13.6 electron volts. In chemistry, people refer to this as the 1s state. The next smallest energy corresponds to L equals 1 and J equals 0, or to L equals 0 and J equals 1. Both of these give n equals 2 or u sub n is a half. When we substitute that in and determine the energy, we get that for both those states, the energy is minus 3.4 electron volts. Those correspond to the 2s or 2p states in chemistry. We could go on, but I'll leave that to you as an exercise. One of the things that I want to mention before we go is that by doing this manipulation that we've done here, we've determined all the possible energies for the quantum description of the hydrogen atom. Before we go, I want to mention that although we've determined the energies, we can also find the full solutions. Full solutions, corresponding to different L's and N's, they have this form here, where there's a constant times r over the Bohr radius raised to the L, times our functions f, times this exponential fall off, and times the spherical harmonics, where the Bohr radius is this quantity that's about 5.3 times 10 to the negative 11 meters. The thing that's left to do in order to completely specify this solution is to solve this recursion relation in general. It turns out that this is something people have done a long time ago, And the general solution of these are given by generalized Laguerre polynomials, and I'll leave that to you to examine in your own time.